Well, good afternoon, everyone. It is Iryna Gureyvch, who is a professor at the Department of Computer Science at the Technical University of Darmstadt. And she's also the director of the Ubiquitous Knowledge Processing Lab, who will talk us about understanding and generating natural language arguments. She's also been elected as ACL Vice President-elect, and also has been selected very recently as ACL Fellow 2020, which would like to congratulate her for these achievements. She's also co-director of the ELIS NLP program. So without further ado, I would like to allow Iryna to give us a talk.
Thank you very much, Sophia. Good afternoon, everybody. I'm delighted to be here today and to talk about computational argumentation. Computational argumentation is a fast-growing field with numerous applications in discourse analysis, summarization, debate modeling, law, among others. So some of you might be familiar with this image. If not, this is an image of a system which was presented about 2 years ago by IBM, and which is an automatic debater called IBM Debater, and which is capable of carrying out a debate with a human. So this system was developed in parallel to the research which I present to you today. And in close collaboration with IBM and other colleagues, I was among the people who have initiated the field about 5 years ago. So why do people love to argue, and why is this an important topic? So let's have a look at Quora, what people respond to this question. When people are engaged in debate, they effectively join together in a search of truth. For thousands of years in many unrelated cultures and traditions, serious thinkers have held that the best way to get closer to the truth, justice, insight, or reality through different types of argument. It is a primary learning method, and even modern science is a sort of one long multi-partner, multi-strand argument over time, which I find a fascinating application if we were able to extract arguments from scientific literature and chain them over time. And finally, arguing is an extremely effective way to gain new knowledge, learn about another person, understand yourself, and just practice communicating. It is exciting. So first, let us define argumentation and relate it to something that many of us are familiar with, sentiment and opinion. The latter is about analyzing people's sentiments towards a topic, and the former is about convincing someone of a specific viewpoint, as you can see in this image. One of the widespread definitions of argumentation is as follows. Argumentation is a verbal, social, and rational activity aimed at convincing a reasonable critique of the acceptability of a standpoint by putting forward a constellation of one or more propositions to justify the standpoint. In fact, the bridge between sentiment and argumentation is still a fundamental open research question in itself. Now let us have a look at a simple argument. An argument is a claim. For example, physical education should be mandatory in schools, supported by reasons. For example, more than 100,000 people died in 2011 due to lack of physical activity and obesity. And there is a support relation between these two statements, and taken together, they are supposed to persuade the audience that the claim is correct. Of course, in reality, the argumentation structures are more complex. For example, we have rebuttals like the attack relation instead of support. In this example, living and studying overseas is an irreplaceable experience when it comes to learn standing on your own feet. We have several premises. The one will learn living without depending on anybody else, which is supporting the claim. And then another one who is living overseas will, of course, struggle with loneliness, living away from family and friends. It is attacking the claim. And another premise, those difficulties will turn into valuable experiences in the following steps of life, which is also attacking the previous premise, and they build a kind of chain. And two attack relations turn the stance of the two premises taken together to a support one. So the main task of argument mining is to convert unstructured text into such kind of structures, which are either tree structures, like in this example, or can also form graph structures. Computational argumentation has a vast number of applications. It is applicable in any area of human life which is concerned with making decisions, because we need to evaluate various options in terms of their pro and con arguments. It is fundamental to persuasion. For example, the doctor might be looking for arguments to convince the patient to adopt a specific pattern of behavior. It is crucial for critical thinking, which is a foundation of any democratic society. And last but not least, I've already mentioned that argumentation is the main technique to generate new knowledge, including scientific work. Our lab in Darmstadt has done a lot of work in the field of argument mining, of which I can present only two pieces today due to some time constraints. And in this slide, I present an overview of the argument mining work done in our lab for those who are interested to learn more. We have worked both on the analysis of arguments within a discourse and on a more information retrieval-oriented setting, where we start with a claim, statement, or topic, retrieve relevant documents, identify argumentative statements and their stance, and then perform fine-grained analysis of arguments. We have looked at research questions in stance detection, argument granularity, multilinguality, quality assurance related to fact-checking as well, argument similarity and clustering efficiency in order to generate argument clusters. And also we have several research works in various application domains of argument mining, like argument search, fact-checking, interactive evidence detection, or dialogue systems. In my talk today, I'm going to cover two research pieces. So one of them is cross-topic argument mining from heterogeneous sources, published in EMNLP and ACL in previous years. And another piece of research is on aspect-controlled neural argument generation, which is work in progress available in arXiv currently. Let me start with the problem definition of argument identification. We are given a controversial topic, like, for example, autonomous cars. And the task of the system is to extract pro or con arguments. And in our work, we work at the level of sentences. So basically, we define this as a sentence level classification task, and extract those arguments from the relevant documents for the given topic, resulting in a list of pro and con arguments for the search topic. The first challenge to be solved in this kind of research work is to create training data, because when we have started doing research on this, there were no existing benchmarks on argument mining. We have several requirements that our annotation scheme needs to comply with. First, it should cover our application scenario and the problem definition of the sentence level argument classification, as I've just described. Second, it should be general enough for heterogeneous texts. And third, it should be simple enough for crowdsourcing, because for the current deep learning models, we need a large amount of training data. So the annotation task should be scalable to obtain a high number of annotations. So in our solution, we define the topic as some matter of controversy that can be expressed with keywords. So the input to the system is a short phrase. And we define an argument as a span of text, in particular in this work as a sentence with evidence supporting or opposing a given topic. So it is important that the sentence contains some evidence. This is what is defined to be an argument. And this is a three-class classification scheme. We have three classes: pro argument, con argument, and no argument. This is an example how the scheme is applied in practice. For the topic nuclear energy, we have a sentence: nuclear fission is the process that is used in nuclear reactors, and so on. This is a definition. Because of this, we attach a label no argument. The second one is as follows: the amount of greenhouse gases have decreased by almost half because of the prevalence in the utilization of nuclear power. So this sentence includes a reason why nuclear energy is good. So we attach a label a pro argument. Then we have another topic of minimum wage, and the sentence is: a study found that minimum wage workers are more likely to report poor health and suffer from chronic diseases. Here, the sentence talks about negative consequences of the minimum wage. This is why this is a con argument. And finally, the last sentence is: we should abolish all federal wage standards and allow states and localities to set their own minimums. So here we have a sentence which expresses an opinion. However, it does not give a reason. And I have mentioned that the reason is something which is part of the argument definition in our scheme. And this is why we classify this as no argument. And the example sets our approach apart from the discourse agnostic stance detection task. So as our data, we construct a corpus by conducting web searches with the help of the Google search engine and retrieve heterogeneous documents like news, online discussions, blogs, so on, for 8 controversial topics, for example, school uniforms. And in our initial annotation study, we employed 2 expert annotators who are graduate level NLP assistants, and they independently annotate 200 sentences for each topic. The average agreement over topics is 0.7 in terms of the kappa statistic, which indicates a sufficient agreement and which indicates that our annotation model is applicable to heterogeneous texts by expert annotators. So the next step is to scale the annotation process up, since we have said that we require a large amount of annotated data, and this cannot be done with expert annotators. So in our initial study, we asked 10 crowd workers to re-annotate the expert annotated data on AMT. And then we merged the annotations of the crowd using MACE, and we compare the agreement of crowds, of crowd workers versus experts. The result is that the crowd workers achieve kappa of 0.7 agreement with expert annotators, which we consider to be a very good result, since it is comparable to the agreement of experts among each other. So this figure gives you statistics of the final corpus with 8 topics, 50 documents each, resulting in 25,000 instances annotated in less than 1 week at the cost of $2,700. And based on this new data set, we now learn a classifier for argument mining across topics. So the classification task is defined along 2 scenarios. One of them is a 2-label task where we classify a sentence as argument or no argument relevant to the topic. And the second scenario is a 3-label task where we classify a sentence as no argument, pro argument, or con argument with regard to the topic. And we use the cross-domain evaluation where we train on n-1 topics and test on the left-out topic. So in our older work, we have developed several neural models for this. One of them is based on transfer and multitask learning, based on LSTMs. And in our latest experiment, we have replaced this by contextualized word embeddings. And the BERT model gives 20% improvement in F1 macro with a total of F1 resulting in 63.2 on a 3-label task, which is a more complex task. In our analysis of results, we find that we still have a gap of about 18% point to the human performance. And in comparing the results on the 2-label task with a 3-label task, we find that the task of argument identification has F1 of 0.7, which is considerably higher than stance detection, having the F measure of 0.62. And what we observe is similar to what has been found in the field of sentiment analysis. In particular, generalizing over topics for stance detection is harder than for argument identification because the lexical cues which are relevant for stance detection tend to be ambiguous depending what is the context of the topic where they are used. So in sentiment, you might be familiar with examples like the cold cola is positive, but the cold pizza is negative. So similar phenomena happens here, and the analysis should be more fine-grained as compared to what we do now at the sentence level. In our error analysis, we find that the model often confuses the stance, like there is reason even for people who oppose the use of marijuana to support its legalization. Here, the word oppose is not used to oppose, but rather to strengthen the topic, and the stance is classified incorrectly. And another observed mistake is the relevance of the predicted sentence due to the lack of domain and world knowledge. For example, in the sentence, all the above gas, also known as the greenhouse gases, may cause global warming and climate change. The correct prediction is pro, and the model classifies this as a con argument. So the argument talks about the negative effects of greenhouse gases and predicts a negative stance towards the topic. However, nuclear energy does not produce any greenhouse gases, and hence, in this case, it is rather an implicit pro argument, but the system is unable to capture this. So in summary of the argument identification research, I'd like to point out that we have proposed a novel annotation scheme which is reliably applicable to heterogeneous texts and simple enough for crowdsourcing. And we have proposed a large new data set for argument classification with 25,000 examples over 8 controversial topics. And our conclusions indicate that we have strong results in a cross-topic setup for the difficult task of combined argument and stance detection. However, stance detection turns out to be more difficult to solve than argument classification and remains a focus of future work. And also we observed that the model fails to capture the topic relevance due to missing world knowledge. Based on our data set, there has been several follow-up works by others. For example, the data set has been transferred to other languages. Other groups have worked on integrating world knowledge into neural models or explaining the classification decisions. And also there has been very interesting work on retrospective labeling by IBM, where they have used our data set to bootstrap a classifier and collect an even much larger data set with that than ours. And though the agreement on that data set is lower than on ours because the data set is noisy, they are able to learn a model which performs better than ours due to having much more data. So now I turn to the second research focus of my talk, which is the aspect-controlled neural argument generation. So what is the motivation for argument generation? Imagine that a politician needs to prepare for a debate, but it can as well be a student who wants to write an essay, or a journalist researching arguments for a particular article. And in such a situation, it may be the case that opponents and journalists may ask tough questions. The ability to anticipate counter arguments is crucial for successful PR. And also it's crucial in order to write a good essay, because a good essay would also talk about the opposing arguments and not only about the arguments in favor of something. And here we think that an assistive system could help to construct counter arguments based on topics and their aspects. And for this, we propose neural counter argument generation. In proposing neural argument generation, we of course build on top of the current state of the art in language generation in general, because it's a particular instance of this NLG task. And here we know that in the recent years, there have been huge improvements due to recent neural architectures like sequence-to-sequence architectures, and more recently, transformer-based language models. And also, I want to mention that we are not the first ones to study the neural argument generation as such. So there has been previous work 2 years ago. However, in that work, the main limitation is that there was no explicit control over the generated argument. And it could be the case that we input an argument and want to generate another new argument, and the new argument becomes unrelated to our input, so it can go in different directions. We don't have the possibility to control the output. And also, these systems also suffered from the limitations which are well known in the domain of NLG, like repetitions of input in generated text. So our main idea is to use conditional generation models and condition the generation on short control codes while training. To do so, our model has to allow for control over at least 3 dimensions. The topic, for example, nuclear energy, the stance for or against the topic, and the argument aspect, for example, health or waste, which represents a very particular facet about that topic. And technically, we adapt the transformer-based CTRL. It stands for Conditional Transformer Language Model, that allows to condition it to certain control codes at training time. So in summary, the main properties of our work are the following. We use a state-of-the-art transformer model for the novel task of sentence-level argument generation, and we allow for fine-grained contextual control of the generated arguments, and the latter represents the main novelty of this work in comparison to prior work. In solving this problem, there are 2 main challenges. So the first challenge is how to identify argument aspects, because there exists no previous work that allows to do so. And the second challenge is, as you know, transformer models are very data hungry, and we need massive amounts of training data which do not exist, like sentences labeled with topic, stance, and aspect. So now I'm first going to talk about the identification of argument aspects. We would like to explain the definition of argument aspect detection with the help of the example on the topic of nuclear energy, and the argument running nuclear reactors is costly as it involves long time disposal of radioactive waste. So first of all, we define that argument aspects are not bound to any part of speech tags. So in previous work, there was a limitation that it could be only noun phrases, but in our work, for example, costly is not a noun phrase, and we can consider such aspects. Second property is that the argument aspects hold the core reason upon which the conclusion of the argument is built. Third, they encode the stance towards a general but not necessarily explicitly mentioned topic that the argument discusses. So in this case, they encode the stance con because the price is high, which is bad, and the radioactive waste is also, of course, bad. It should be noted that the topic is not explicitly mentioned in the sentence. So now the next question is how to generate training data for argument aspect classification. And here we propose a novel two-staged annotation scheme to tackle this difficult sequence tagging task. So in the first step, we employ two experts who are NLP research assistants and who perform a free span level annotation task of the aspects. They annotate 800 samples from 4 topics, and we compute the agreement, which results in Krippendorf's alpha of 0.38, indicating that the agreement is moderate and not very high, and that the task is fairly difficult. So that also means that this approach cannot be scaled to crowd workers. So because the task is just too hard. So here we develop an idea which uses this expert annotation to build a recommender for the crowd workers. So in the second stage, we train such a BERT-based ranker for aspect recommendations based on the expert annotations. And then we look at the recall of aspects and find that the recall is pretty good. So in topic, it is 0.84 at recall of 10, and cross topic, it's 0.81 at recall of 15. So we set these thresholds to present the recommendations to the crowd workers, and the interface looks like this. So instead of performing a span labeling task, they select the relevant aspects from a list which the system presents to them. And if the aspect cannot be found in the list, we also allow them to label freely a new aspect. So the resulting data set has much higher agreement. We have Krippendorf's alpha of 0.67. This is 12% point more as compared to the study without a two-stage approach. And this way we can collect a data set of about 5,000 training instances with argument aspect labels. And we evaluate this against the majority baseline and a BERT-based ranker, taking the top 2 highest ranked aspect as prediction. And we find that a BERT-based sequence classifier yields the F measure of 0.71, which we consider to be feasible in order to be applied for the task of training data generation in our neural argument generation approach. Now, let me turn to the second challenge, how to create training data for natural language generation. It is completely clear that we cannot annotate this amount of data manually, so we propose a semi-supervised approach where we first retrieve up to 1.5 million documents for each of our 8 topics of the sentence level argument identification dataset that I've presented in the first part of my talk. And we retrieve 1.5 million documents, each from 2 data sets, Common Crawl and Reddit comments. And we treat these data sets separately and train 2 generation models for later comparison of results. We apply automatic sentence splitting on all documents retrieved from the sources, and we classify the sentences into no argument, pro argument, and con argument. And since we are not interested in non-arguments, we just remove them from the data. And finally, we use our aspect detection model, which I've presented before, to identify all aspects of the remaining arguments automatically. Finally, we group all arguments with the same topic, stance, and aspect and concatenate them into our final training document. And to prevent the documents from being too small, we set a lower limit of 15 sentences per topic and an upper limit of 1.5 thousand sentences so that we do not overfit on large overrepresented aspects. Next, the document texts are split by the maximum sample length, and each sample is prepended by the control code, that is the topic, the stance, and the aspect. In the shown sample, this would be nuclear energy as the topic, pro as the stance, and base load power as the aspect. Contrary to the original CTRL architecture, we allow for control codes of arbitrary length. Finally, at inference, we pass a control code to the model, which generates an argument following that control code. For example, we pass the control code nuclear energy pro base load power, and the model generates an argument with this context. To analyze how well the trained Reddit and Common Crawl models perform, we generate approximately 8,000 arguments from each model. And our reference data consists of around 700 arguments for all 8 topics crawled from human debating websites on the web. And then we compare the generation model against an upper bound retrieval approach. The retrieval approach retrieves arguments from the training document for all control codes used at training. And of course, the retrieval approach has 2 advantages. First, all retrieved arguments are human-made, while our generation model-based arguments are not human-made. And second, all aspects used in the control code are certainly to be found in the argument in the retrieval-based mode, while this is not necessarily the case for the generated arguments. In the results, which is the table depicted in the lower right corner, we can see that our model performs a bit worse than the retrieval-based baseline. However, this performance is still impressive in our opinion, given that our model is a fully automatic one. So it shows the strength of our architecture. And also it shows the success in generating sound aspect-specific arguments with our approach. In the motivation of neural argument generation, I've already introduced the task of generating counter-arguments. Counter-arguments describe the same aspect as the initial argument, but they have a switched stance. And here in this example, we can have a look at the arguments automatically generated by our system, given the input arguments. School uniforms are expensive and affect the pupil's individuality. So there are 2 aspects here, the price and individuality. And we switch the stance from con to pro, and the resulting arguments are as follows. The cost of the uniform is not that much more than a regular shirt and shorts. And the second one, the uniform is a symbol of unity and identity, which helps to foster an environment where students can feel comfortable about expressing their own individual style. So as you can see, the arguments look quite human. The model, nevertheless, has some limitations. And as I said, this work is still in progress, so we are working on some of the aspects. First, transformers need a massive amount of training data. So we only had 8 topics for which we used 1.6 million arguments. And there is no possibility to use manually labeled data of higher quality in such a scenario. However, based on our semi-supervised approach, there are multiple errors from sentence splitting or incorrect stance argument classification that propagate through our training data, and we need a higher quality pre-processing pipeline to mitigate these negative effects. Also, the model is computationally expensive, so it needs at least 16 GB GPU memory to run, and the training took 5 days in our case on a Tesla V100. And the generation of a single argument takes up to 15 seconds, which is a way too much time for a single sentence. So in summary, I have presented a novel method of aspect-controlled neural argument generation, and we have achieved high argument quality comparable to human-made arguments. We have shown that conditioning the model on the aspect, topic, and stance is essential, and have proposed a new high-quality argument aspect data set with 5,000 examples based on a novel argument aspect annotation approach. And the aspects can also be used in future work in order to label the clusters of arguments. There are multiple directions for the future work, for example, to improve pre-processing, to integrate argument generation in interactive dialogue systems, and also to introduce more efficient models in order to reduce training and inference time. In summary of my overall talk, the take-home messages could be as follows. Argument mining research has diversified into a set of subtasks, each drawing attention in their own regard. So the number of papers in this area of NLP is constantly increasing, and the types of work that you can find are about argument retrieval and stance detection, argument quality assessment and evidence verification, argument similarity and clustering, and argument generation. And there's a huge amount of future work possible, like constructing better models, proposing novel data sets, integration with interactive settings, and so on, so on. So one particular example that we explore in our current work is a further development of this technology under automated fact-checking. So here the main difference is that the input is not a short phrase like in the work I have presented today, but a whole statement like Israel caused flooding in Gaza by opening river dams. So it's much more complex. And the system conceptually proceeds in a similar way. It retrieves relevant documents, and the relevant snippets from those documents, classifies them in terms of stance. And then it also needs some reasoning and aggregation capability in order to infer from these relevant snippets if the original claim is right or wrong or something in between. If you're interested in our research, I'd like to mention that all of the data sets and the software from the work I have presented today and related research at our lab is freely available, as you can see in this table. And there also exists a web-based free version of this system, which you can experiment with if you like, by inputting a topic, for example, Brexit or whatever topics you currently have on your mind, and looking at the arguments that the system can output based on the common crawl. With this, I thank you very much for your attention, and I am very much looking forward to the discussion, and would also like to mention that among the audience, there are 2 members of my lab, Johannes Daxenberger and Benjamin Schiller, who are the main authors of this research, and they will also be looking forward to answering any questions that you might have. Thank you very much for your attention.
Thank you so much, Iryna, for the very interesting talk. So now the floor is open for questions, and I failed to mention in the beginning, I would like you to ask your questions using chat, and then I will channel the questions to Iryna, or basically she can see it as well. So who wants to start first? So while people are waiting and thinking about the questions, perhaps I should start with a very more general question, which would be very interesting to elaborate. You mentioned that still stance is something extremely difficult and complex to do. Perhaps you can tell us a bit more your thoughts. Why is that?
Yeah, I think the stance is very contextually dependent. That's the main reason, which I also mentioned in my talk. Depending on the topic, the lexical cues might have an opposing stance, and this might lead to misclassification, which happens quite a lot. And maybe Benjamin, who has worked on this problem, could also add some insights from the error analysis. Benjamin?
Yes. To be honest, I can't really add much to what Iryna already said about this. So the main reason here is are probably these lexical cues that sometimes just confuse the model with what we have seen in the example, oppose in front of something, and the actual sentence is actually in favor of the topic. Yeah.
Any questions? There is a silence in the audience. I know some people have been working on arguments and stance, perhaps, or great. So we have a question from Philip Ventiroso to what about nested arguments? Support may need another supporting argument, otherwise may not be enough of an argument. So if you've looked at nested arguments.
So in this work, unfortunately, no. So we did not consider more complex argument structures. So we work on the sentence level, as I said. We have some other work which looked at arguments at the discourse level, where we analyze a student essay and convert the student essay in an argument tree, basically. So in an argument tree, you can have such structures where a premise supports or attacks another premise. But in this work, we have this web search engine in mind. So like sentence retrieval scenario, basically. And the main challenge here is how to operate across heterogeneous discourse types and across different domains. So because of this, the first step is to have a more simple model and to be able to solve this setting. And in future, for example, I have mentioned the fact-checking research. So that research could be used at the level of retrieved arguments. So with this technology, we could validate basically the argument. So the argument that we have retrieved would become a claim, and we could find evidence in support or attacking that claim.
We have another question from Hrisa. Again, on the stance related topic, would adding dependency or syntax information or modeling text as a graph help with regards to identifying where stance related terms refer to within the sentence?
Yeah, so I don't have an empirical answer to this question because we have not done this work, but my personal opinion is that it could definitely help. Something similar has been done in the domain of sentiment analysis, and richer structures could make the representations more fine-grained, and that would counteract on this problem of context dependence. Yeah. So basically, then the question would become how to inject this kind of knowledge into neural models, because the neural models operate end to end. So there should be some way how to inject that knowledge.
Well, maybe while other people are saying, oh, here it is again, Coran. Have you considered using arguments presented in previous sentences for classification of the current sentence? So something like identifying argument shift.
So this is a clever idea, and this could be done, but we have not done so. So in our work, we collect the data in such a way that the annotators classify the sentence out of context. So one could, of course, perform an experiment where the annotators classify the sentences in context, but that would make the task more complex and also more expensive, of course, in crowdsourcing, because people need more time to analyze this. So I don't know if one would have enough benefits in terms of the trade-off between the effort that needs to be invested and the benefit in terms of the result quality improvement. And also, I'd like to say that argument annotation is a very difficult task. This is because this task is demands quite high intellectual resources, and humans are actually not a good model for this task. So it's not something we do intuitively, but we are trained a lot, both at school and at the university, to identify and to produce arguments. So we need to be trained for that. And when we use crowdsourcing for data set generation, of course, we have very limited possibilities how to train the annotators. So the task is hard, but it should also be simple. So I think if one wanted to perform this research, we would also need to check if the agreement is good enough, because I can imagine that the agreement would drop if the task is more complex than our sentence level task out of context.
I just want to follow up while people are thinking their questions. This perhaps follows from your initial discussion about having a two-way or three-way, more fine-grained analysis annotation. And obviously, the more you're doing a fine-grained annotation, it becomes more difficult and more complicated to solve the problems. I guess the same thing.
Yeah, so you are completely right. We also have one paper published together with a group of Hinrich Schütze this year in AAAI, where we looked or formalized the problem of argument classification as a sequence labeling task instead of sentence level task. Of course, it is the case that one sentence could contain two arguments, for example. So our current model that I was presenting today is not capable to capture this. This is why we had the idea of sequence classification as our formal framework, and then we can extract more fine-grained units. But in practice, so we found that when such argument nuggets are extracted, it's very hard for the humans to make sense out of them when they are taken out of their natural context in the sentence. And we think it can be used to highlight the argument nugget or the argument core within an argument sentence. But this is an example where the fine-grained level is not necessarily a huge benefit. Of course, the annotation, the crowdsourcing is also much more expensive. So we need much more training instances, and the task is more difficult for humans. So they need more time, it becomes more expensive. So at the end of the day, we were not convinced that the effort is worth it. You know, it's interesting research, but for using this in a practical search engine, probably the effort of creating all the training data and going through all the trouble just to highlight the nuggets of the argument would be too much.
Yeah, I think it's a kind of it's a good observation about other tasks that sometimes when they become very fine-grained, one has to think what are the benefits. We have two questions. One is from Philip Charles Mentiroso. Would you say that the most difficult case of argumentation to label positive, negative, and neutral are the non-negations? For example, nuclear energy has not been a threat.
Yeah, it's definitely very hard. So I don't know if it's the most difficult, but I think these things like negations present many challenges. I wonder if Johannes or Benjamin have a comment on this, since they have looked at the data and might be able to say something about the challenges and how many negations we have in the data and things like that. So do you have any addition?
I didn't have a look at this empirically, to be honest. My intuition is that it would work in some cases, but probably not in all. I'm just about to try it out, what the model would do with the example sentence. So maybe I can report in 2 minutes.
Good. So we may discuss the next question first, and then could come back to this empirical investigation.
Yeah. So the question is from Nick Wharton, who says, is it an actual challenge to the reliability of the generated arguments when you rely on evidence provided in sentences in the data? Because there may be a proportion of instances where the evidence provided is unreliable or biased, or a commonly held misconception of the topic in question. So it's again, I guess, so is any a way to fact check evidence provided across several sources?
Yeah, I mean, fact checking is a line of current research, but it's even more hard than our scenario, because we need to analyze complex claims. So it becomes much more complex to retrieve and aggregate evidence. Another point that the question is making is that the arguments are retrieved from common crawl. So our data is fairly noisy, since this is crawl of the web in the wild, so to speak. And of course, the quality of the data very often is not ideal. So we don't explicitly treat this research question in this work. So our annotators do not perform any quality related annotation, but in some other work, we have worked on automatically measuring the quality of arguments across several dimensions. I guess Johannes has found something interesting, judging by his face.
Yeah, so this example sentence actually works. Nuclear energy has been a threat, is recognized as a con argument, and nuclear energy has not been a threat, was recognized as a pro argument. So for nuclear energy, I assume, so I was positively surprised. First of all, I assume this is because at the sentence level, yeah, this is giving enough context for a contextualized model, like the transformer one that we're currently using to deal with negation. It probably doesn't work in all cases, but for simple cases like that, it does work. So
yeah, I would conjecture that this depends on the composition of the training data. So one needs to mention that we have quite many training examples for each topic. So we have a very low number of topics, 8, but a huge number of examples for the topic. And this particular sentence, nuclear energy has not been a threat, would probably refer to like arguments represented quite a lot in our data, because it's a common argument. And I think that due to the richness of the training data for this topic, the model is able to resolve this. But I think this is like my intuition is this is not very systematic.
I can try with a different topic, but I think you're right, Iryna. Yeah.
We have about 4 minutes for any other question. Okay. Just very briefly, what actually made you focus on those 8 topics, or how do you think by expanding on using more topics would affect your results? You said you focus on 8 topics and they would be more in depth, but what about if you're working in different domains or different topics and more shallow approach rather than depth, how this would affect your work?
Yeah, we have looked at that, Sophia. Johannes has looked at this. So Johannes, would you like to respond?
Yes, so Iryna already mentioned to generate lots of training data, even using crowdsourcing is obviously expensive, so we were limited in the number of topics that we considered. However, we have also looked at a broader range of topics around innovation, mobility, and such things, annotating a fewer number of examples per topic. And the result is that the more topics you annotate, the better the model learns to generalize and actually abstract away from the topic. So we are, as Iryna has shown, we are evaluating in a leave one topic out fashion. So we always test on an unseen topic, and the more topics the model sees at training time, the better it generalizes to unseen topics, also regardless of, you know, domain or the general focus of those topics. So you need more than 8 topics, but you don't need thousands of topics. Maybe something around 100 would be good to generalize.
Thank you. Couple of minutes, folks. 1 minute. Well, I think, oh, well, here is a very quick one for one minute. I'm not sure if you have to say anything about the IBM's project debater. Is it relevant to your work? I thought it was, but anyway.
Well, it's a great project. So we collaborate with Norm Slonim and his group. However, we have different foci because the work I've presented here is a search scenario, so information management and generating arguments and stuff like this. And the IBM debater is a dialogue-based scenario. So these have different objectives. However, there are many synergies between their work and ours. So for example, they have developed a model for automatically measuring argument quality. And we have applied this model to evaluate the quality of the arguments generated by our system and the quality of human generated arguments automatically. So I think there are many implicit overlaps, though we tackle 2 different scenarios in the area of argument mining. And also, since they are oriented towards a speech-based system, it has different aspects that we do not cover. So for example, when the system speaks, it needs to be convincing. So this is related to speech generation, expressiveness, prosodic features and stuff like this, which we do not look at in our work at all. And vice versa. So our technology can be used for their debating system to retrieve arguments that fit a particular context. So this is the interrelation between these 2 lines of research.
Well, thank you, everyone, and thank you very much to Iryna and her team for a very interesting talk. It was very enjoyable. Goodbye, everyone. So the slides are recorded and there is a video if you want to see them. Thank you again, Iryna, for your time and the interesting talk. Bye-bye.
Yeah, you are very much welcome.